Math 1332, Chapter 3, Symbolic Logic, Section 2, Truth Tables, Video 5, Building Truth Tables, and Truth Table for Biconditional. Originally, this is going to be two videos, one that just gave you the truth table for biconditional, but it dawned on me that the best way to justify what that truth table is to actually show you how to build a truth table for a more complicated compound statement based on previously existing truth tables. Now, you might be thinking, but a biconditional just involves one connective, the double-headed arrow, with a simple statement on both sides. So how is that a more complicated, more complex compound statement than just say conjunction, disjunction, or conditional? Well, the answer to that lies in what a biconditional actually means. So let's review the tools that we have so far at our disposal, figure out what a biconditional really means, and then use that to develop a technique for building more complicated truth tables. All right, so here's the tools that we have so far for building truth tables. We have our hierarchy of connectives, which is not going away. First, parentheses, second, negation, third, conjunction/disjunction, fourth is conditional, and fifth is biconditional. And we also have four basic truth tables at our disposal. Let's see if I can find them. Let's see, that's one of them. Our first basic truth table is negation. And although you can memorize the truth table, I strongly stress and highly recommend memorizing the rules. The rule for negation is it changes the truth value of a statement. So if a statement is true, its negation is false. But if a statement is false, then its negation is true. The second basic truth table that we built was for conjunction. And there's the truth table, but again, I highly recommend knowing the rule. Conjunction is true only when all of its simple statements are true. In other words, when you have a conjunction and both halves of it are true, then the conjunction is true. And more importantly, that is the only time it is true. The rest of the time, a conjunction is false. The third basic truth table that we discovered was the one for disjunction, the one for the word or. Again, you can memorize the truth table, but I would really understand the rule. The rule is disjunction is false only when all of its simple statements are false. So in other words, in your truth table, when both P and Q are false, that is the only time an or statement, a disjunction, is false. Otherwise, a disjunction is true. And then the final truth table that we came up with was for conditional. And this one was not as intuitive, but if you really think of it from the broken promise perspective, it's pretty straightforward. Conditional is false only when the antecedent is true and the consequent is false. This is what I alluded to as the broken promise, meaning that the only row where a conditional is false is the second row, when the antecedent, the part to the left of the arrow, is false, and the consequent, the part to the right of the arrow, is true. I said that backwards. When the antecedent, the part to the left of the arrow, is true, but the consequent, the part to the right of the arrow, is false, that's your broken promise. That's when your if-then statement was a lie. In any other situation, the conditional is true, either when both halves are true or when the antecedent is false. When the antecedent is false, that means your if-then statement doesn't even apply. Just a reminder what that means. If I say something like, if it rains tomorrow, then we'll go to Six Flags. Let me rephrase that. No, we'll go with that. If I say, if it rains tomorrow, then we'll go to Six Flags, which would be a silly thing to say, then did I make any commitment under the condition that it doesn't rain tomorrow? I did not. I only made a commitment under the condition that if it rains tomorrow. If it doesn't rain tomorrow, meaning that the antecedent is false, then there's no way I could have lied to you because there's no promise that I made under those conditions. A conditional only makes a promise under the premise that the antecedent is true. And if you don't follow through with that promise, in other words, if the consequent is false, then you broke your promise and your conditional was a lie. It was false. So those are the tools that we have, and we're going to use those to figure out the truth table for biconditional. But first, we need to talk about two things, one thing in general, one thing specifically. How can we use these these tools, these basic rules that we have so far, and our hierarchy of connectives to build truth tables for any compound statement. And what about biconditional? What do I keep saying when I'll tell you what biconditional really means? Well, let's talk about what a biconditional really is. The phrase if and only if is shorthand for expressing two conditionals simultaneously. Allow me to demonstrate. For example, consider the compound statement, I have a job if and only if I have a car. That is a very compound statement. It has a conjunction in the middle. The conjunction is right here, and on either side of that conjunction, I take that back, I'm getting ahead of myself. But there is a conjunction in the middle. But the compound statement, I have a job if and only if I have a car, is really the following pair of conditionals joined with a conjunction. If I have a job, then I have a car. And if I have a car, then I have a job. The conditionals match, it's just that the antecedent and the consequent trade places. In the first one, in the first conditional, let's make sure this gets highlighted. The antecedent is I have a job, and the consequent is I have a car. But in the other conditional, the antecedent is I have a car, and the consequent is I have a job. And right smack dab in the middle is a conjunction joining the two conditionals. So it's called a biconditional because it's a conditional going in two directions, from left to right and from right to left. And when I say that, I mean in reference to the original biconditional. From left to right, the conditional is if I have a job, then I have a car. And from right to left, the conditional is if I have a car, then I have a job. Well, symbolically, we can write a biconditional as something that it's logically equivalent to. Now, I put the phrase logically equivalent in quotation marks because it's something that we'll define in the future. But for now, let's just accept that we can kind of use it without having formally defined it. But symbolically, we can say that the conditional P if and only if Q is logically equivalent to the following compound statement. Following compound statement. And sometimes when I type the double-headed arrow, I will type it this way with the less than, double line, greater than symbol in an attempt to type a double-headed arrow. But it's logically equivalent to the following, and we're going to draw this. Let's think about it. Let's build it. If in our original biconditional, we call I have a job P, and I have a car Q, and of course, if and only if is the double-headed arrow, then how would we translate the longer sentence that's highlighted in pink? Well, the and is the primary connective. You can tell because it's surrounded by commas. So we would have a conjunction parked in the middle of this. On either side of the and, we have another compound statement. And remember the rule. If you are looking on either side of a connective and you see another compound statement, then it goes in parentheses. And we have one on both sides. On the left side of and, if I have a job, then I have a car would translate into P conditional Q, or P pointing to Q. And on the other side, if I have a car, then I have a job would translate to Q conditional P, or Q pointing to P. Hence, to determine the truth table for the biconditional, we're going to build the truth table for this compound statement. Now, we haven't built a truth table for such a size compound statement. This compound statement has three connectives. It's got two conditionals and a conjunction in the middle. All of the other truth tables that we've had so far have just had single connectives in the middle. This one, let's put it in blue. This one has just a conjunction. This one has just a disjunction. This one has just a conditional. We have yet to build a truth table for something involving multiple connectives. Well, now's the time to learn how to do it. To build a truth table for a compound statement that involves more than one connective or negation, we use the hierarchy of connectives to determine the correct order to build the columns for the truth table. Now, I'm not going to rewrite the hierarchy of connectives here, but we will just go through it one at a time. You should know that parentheses is first. Excuse me. According to the hierarchy, we go to the parentheses first. Since there are two parentheses that do not involve each other, you don't have one inside of another, we address them from left to right. Remember, we're building a truth table, which is going to start with a column for P and a column for Q, along with all the possible combinations of truth values that we've talked about before. So after those columns, the first column will represent the conditional in the first parentheses. So I'm going to write first over this because our hierarchy says go inside that parentheses and see what you see. Well, there's only one connective in there. Guess where we're going to go next after that one? Well, there's still a parentheses. So the second column will represent the conditional in the second parentheses. And guess where we go after that? Well, this completes the parentheses. Looking outside the parentheses, the third and final column will represent the conjunction. So I now know that my truth table is going to have 5 columns. It's going to have one for the letter P, one for the letter Q, and then one for each of the connectives. And when we get to the last one, we'll have the completed truth table. I've already got a truth table set up for 5 columns here. And notice that I've got the compound statement written on top with the order in which we're going to build it. But however, we already know that, one second, folks. Sorry, I forgot what was under this white box down here and I had to look at it real quick. All right, so we always start a truth table the same way. We start with one column for each simple statement. And since our only simple statements are P and Q, that's our first 2 columns. And we populate those 2 columns with every possible combination of truth values without rehashing that story. They will always be true, 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 false, false, true, false, false. Technically, the order of the rows doesn't matter as long as you have all 4 combinations of truth values, but me and the homework and I will always have the rows in this order. Now, how do we complete the truth table? Well, here's how. To complete a column, you ask yourself 2 questions. Oh, I'm sorry, I didn't mean to expose that yet. According to the hierarchy, we've already decided the order in which we're going to complete this truth table. The first column we're going to complete is for the conditional in the first parentheses, P pointing to Q. The second column we're going to complete is for the second conditional, Q pointing to P. Remember, we've already determined this based on the hierarchy. The third and final column will be the column for the conjunction, but here's where you have to be careful. When you write a connective, you have to write something to the left of it and something to the right of it, not for a negation, but for a connective. So if you're not sure what to write, ask yourself, what is immediately to the both sides of it? For this conjunction, the thing immediately to the left of it is that closed parentheses, which means what I need to write to the left of this is that parentheses and its content. And the same thing for the right side of the conjunction. The thing immediately to the right side of it is an open parentheses, which means I need to write that parentheses and its contents. So as you can tell, that matches the entire compound statement we're trying to find out the truth table for. Okay, now that we've got the columns labeled, and now it's time to undo this thing down here. To complete a column, and we're going to complete them from left to right. I think because of the mirror image that went from right to left. But to complete a column, ask yourself 2 questions. Number 1, which rule will I use for that column? This is where the basic truth tables come into play. Number 2, which previous columns will I apply that rule to? All right, let's begin. First column, which is technically the third column, but we're not calling the first one first to the second one second. All right, so for the first column, the rule that I'm going to use Sorry, I had to pause to sneeze. I'm trying to get better at pausing for things that you don't need to see. But the rule we're going to use for that first column is the conditional rule. Why? Well, just look at it. That column contains this conditional. Now, you don't have to do this, but one thing I would recommend is when you are completing a column, below it, I would just briefly write the rule using as few words as possible. It's not critical to do this. You need to at least think the rule, but it's a good idea to have a visual location to see it. What is the rule for conditional? Well, the shortest way I can write the conditional rule is false when T points to F. That's a very short version of this last one. The conditional is false only when the antecedent is true and the consequent is false. But that is the briefest way I know to summarize the rule for conditional. False when T points to F. So that's the rule I'm going to do. Then I have to know which previous columns to do it to. Well, to locate the columns you're going to do it to, all you have to do is look on both sides of your connective. I need the column representing P and the column representing Q. Here they are. Then I'm going to apply the rule. The rule says I'm going to write false only when T points to F. I have P pointing to Q. And if it helps, draw that arrow there, which means I'm looking for T pointing to F. In which row would I have T pointing to F if I drew arrows? You don't have to draw these arrows, but if it helps you locate T pointing to F, I would do it. It's going to make it a little sloppy, but if it helps, do it. Which row has T pointing to F? The only row that has T pointing to F is this one. That is the only row that follows the rule, and the rule says when you see that, the result is false. So we're going to put an F here. Now, that is the only row where we have T pointing to F, so that is the only row in this column where it's false, which means the rest are true. Now, some of you might be thinking, all you did is rewrite the truth table for conditional, and you're correct. But sometimes it won't always be just that, so it's a good idea to know how to play out your rules. All right, let's clean this up and move to the second column. For the second column, we've already decided that it is going to be the column for the conditional Q pointing to P. So we're going to repeat the same things that we did before. In this column, ask yourself two questions. Question number one, what rule am I going to use? Since the second column is a column for a conditional, we're going to use the exact same rule that we used for, let me just do this, for the first column. That rule being false when T points to F. And again, you don't have to write that rule down there, but if it helps, write it. So that's what we're going to do. Now, which previous columns are we going to do it to? Well, the Q column and the P column. Now, this is where you have to be really careful, and this is where drawing extra arrows can help. Which previous columns do we need to look at? The first two. Just for a moment, I'm going to cover up the column that we just created, the first column. Now, if you're doing this on paper, I wouldn't recommend scribbling over it because we're going to need to refer to that column. But what you can do is say put a pencil over it or a marker over it or a piece of paper over it if it obstructs your view. If you can do what I'm about to do without covering it, then more power to you. But for now, we're just going to cover it up. All right, so we need to look at the Q column and the P column in order to figure out this second column. So I'm going to highlight that. But here's where you have to be ridiculously careful. It looks like I got a stray mark down there. Let me see if I can erase that real quick. There it goes. Okay. All right. So here's where you have to be really careful. At first, you might be thinking, I'm going to get the exact same results I just got for the previous column. This one here. But we won't because in the second column that we're figuring out, who is pointing to whom? Q is pointing to P, not the other way around. So in order to help me play out the rule correctly, in the first two columns, I'm literally going to point Q to P all the way down. Now, you don't have to draw these arrows, especially if you do the other ones earlier that I erased. But when you're evaluating the truth value of a conditional using previous columns, and the previous columns are not in the same order as they're written. In other words, I have Q pointing to P. So over here, Q is on the left, P is on the right. But over here, Q is on the right and P is on the left. If the columns that you're referring to are in the reverse order that you see them, I would highly recommend drawing arrows from right to left to help you play out this rule. So question, over here, in which row do we have T pointing to F? Because that's what the rule is looking for. Hint, it's not row 2. The only row where we currently have T pointing to F is actually the third row because we're pointing from right to left. And according to the rule, whenever I see T pointing to F, that means the truth value of the conditional is false. So in this current column in the third row, our conditional is false. That is the only row where we have T pointing to F for this column. So that is the only row that comes out false, which means the rest of them are true. Now, if that kind of threw you for a loop, I would back up the video and watch it again. But just be careful when you're evaluating a column for a conditional, which reads from left to right, but the columns that you're referring to are not left to right, they're right to left, like they were over here. That's where you have to be really careful looking for true pointing to false, which is the broken promise, which means the conditional is false. All right, let's clean this up. All right, and now let's figure out the last column. For the last column, we'll put it in blue just so it looks a little bit different. All right, so for the third and final column, we're going to do the same thing as we did before. We're going to ask ourselves 2 questions. Which rule are we going to use? And what are the previous columns that I will apply that rule to? Well, let's see. The third column is a conjunction. And what is the rule for conjunction? Do you remember? The rule for conjunction is it's true only when all of its simple statements are true. So what is the briefest way that we can say that? True only when all of its statements are true. We'll say T only when all T's. That's a good simple way to summarize the rule for conjunction. True only when all T's. All right, so that's what we're going to do. Now, what are we going to do it to? In other words, which previous columns do we need to allude to? Well, the columns that refer to the statements on either side of the conjunction. The statement on the left side of the conjunction is P pointing to Q, which is the first column. The statement on the right side of the conjunction is Q pointing to P, which is the second column. Now notice that I'm not using the P and the Q column at the beginning. If it helps, cover them up like we've done before so that they don't interfere. That was not supposed to look like that. It was supposed to look like this. There we go. But being off to the left, they're not really in the way. In other words, the 2 columns I need to refer to are next to the column that I'm filling in. But for consistency's sake, we'll just cover up the columns that we're not looking at anytime we're populating a new column. All right, so I know what I need to do. Write T when I see all T's, and I know which columns I need to do it to, the second and the third columns. Excuse me, the first and the second columns, so that we can calculate the truth values for the third column. All right, so looking at the first and second columns, in which rows do we have all T's? We have all T's in the first row, and we have all T's in the last row. Those are the only rows that follow that rule, which means those are the only rows in which our last column will be true. The other 2 columns are not all T's, which means I'm not going to write T in the third column, which means I write false. All right, let's clean this up. At this point, we've completed the truth table for the compound statement P conditional Q and Q conditional P. So here's what we know. We know that when P and Q are both true, this statement is true. When P is Q and true or false, that statement is false. When P is false and Q is true, the statement is false. But when P and Q are both false, then the statement is true. That's what the results of this truth table mean. But remember, the whole reason we did that truth table is because that compound statement was logically equivalent to the biconditional, which means that the truth values for the biconditional are the same as the truth values in the previous truth table. Without going back, they were T, F, F, T, and therefore I present to you the truth table for biconditional. This is the fifth and final basic truth table. It will be added to the list of truth tables that we have already for negation, conjunction, disjunction, and conditional. And as with all those other tables, you are welcome to memorize the collection of T's and F's that you see here. However, it is much easier to come up with a rule that describes when to do what and when to do something else. Now, this is the only truth table, aside from negation, where there is no clear-cut majority in the last column. In other words, over here, it's not mostly trues or mostly falses. In the other ones, it was. Just as a reminder, let's go back to them. The conjunction was mostly false. The exception was when was it true. The disjunction was mostly true. The exception was when was it false. The conditional was mostly true. The exception was when was it false. But for the biconditional, it is not mostly true. It is not mostly false. Half the time it's true, half the time it's false. So how are we going to come up with a rule that states when to say true or when to say false? Well, we could pick either when is it true or when is it false. Let's focus on when is it true. Here's a true when both P and Q are true. Here's a true when both P and Q are false. So is there anything we can say about the truth values for P and Q in the first and fourth rows? Yes, there is. The rule for biconditional is a biconditional is true if and only if both halves of it have the same truth value. In other words, when both halves are true, the biconditional is true. Or when both halves are false, the biconditional is true. When they match, it's true, and vice versa. I guess you can make a rule for when it's false. They're false. That's what's supposed to be a green highlight. They're false when both halves are different. So you got a choice of rules here. You could use both of them as one big rule. Biconditional is true when both halves are the same. Biconditional is false when both halves are different. But if you know one, then you pretty much know the other. All right, one last comment about this. In this sense, the biconditional is somewhat stating that the truth values of its halves are equal. I'm a biconditional. I'm true because the guys on both sides of me are matched. They're equal. They're either both T's or both F's. So you can almost think of the biconditional as an equal sign. And then whether it's true or false, it depends upon whether or not both sides of it are equal. All right, and that wraps up the basic truth table for biconditional. The next series of the next few videos in the series are just going to be working examples because trust me, these take some practice.